All right, welcome back, class. We're in a new week. As before, I want to spend a little bit of time kind of reflecting back on some of the important points we learned last week, which mostly dealt with quantum indistinguishable particles and elucidating the distinction between particles that are bosonic and fermionic. We actually employed those different quantum statistics to understand heat capacities in certain types of materials. So we worked out simple theories for the heat capacity at low temperature of a metal, so a collection of electrons. And 2 weeks ago, we actually had worked out a theory for the capacity of a semiconducting solid, where the heat capacity was dominated by bosons, or in this case, phonons. We arrived at a theory for that too. And we've shown last week a number of times that at high temperature, where high needed to be specified relative to the energy gaps in the system, that classical physics dominates and those distinctions between bosons and fermions don't matter. So I'll first review that briefly, and then we're really in a position to reflect more largely and more universally, more generally, on what we know about indistinguishable or non-interacting collections of particles. There's a result we've quoted a number of times, the ideal gas law, which tells us about how things like the pressure and the temperature and the volume of independent particles are related. But something we have neglected and not discussed nearly enough is what the chemical potential looks like for a set of independent particles. And so we're going to talk about that today. We're going to derive the form of the chemical potential for a non-interacting system, and actually show how that form underpins quite a lot of the chemistry you're taught very early on. Namely, it underpins how we think about equilibrium constants, solubilities, things like that, which are essentially expressions of where mass spontaneously flows, where molecules or matter spontaneously flows. This statement of mass, or this sort of notion of mass equilibrium, we'll talk about in the context of reactions first. And next lecture, that'll put us in a position to talk about mass equilibrium, not of a molecule changing its state, for example, or changing where it is spatially, but rather changing its phase. And this will then begin a really new set of discussions where we consider phase transformations, the statistical mechanics and thermodynamics of phase transitions, which we'll see shortly next lecture, or in a couple lectures, really cannot be treated through the lens of non-interacting particles. And so that will force us actually to confront techniques associated with thinking about interacting systems. But let's not get too far ahead of ourselves. Let's remind ourselves where we've been so far. So last set of lectures, we really focused on quantum mechanical systems, and specifically those systems which were non-interacting and indistinguishable. We discussed that there are essentially two fundamentally distinct kinds of indistinguishable particles, so-called bosons, which, for example, are, one example of which would be a photon. We worked out that the probability of a boson occupying a given energy eigenstate, labeled I, follows the so-called Bose-Einstein distribution, which depends on the energy level of that state, epsilon I, the chemical potential that is set, because this is a system where the total number of particles can fluctuate. That compared to -1 and inverted gives me that Bose distribution. If I plotted, let's move all this over to give me some space. If I plotted that distribution as a function of the energy of that level, when the chemical potential that I've set is equal to that energy level, I find something kind of odd, which is that all the particles will collapse into that state. And farther away at higher energies, I have an exponential decay of the likelihood of occupancy in that state. So this infinite piling up of particles in a specific energy level is known as Bose-Einstein condensation. It's a peculiarity or a consequence of bosons admitting any occupation number in a given energy eigenstate. Those behaviors are to be contrasted with the behaviors of fermions, for example, electrons, whose average occupation of some ith energy level is not a Bose-Einstein distribution, but a so-called Fermi-Dirac distribution, which looks incredibly similar. Depends on the energy of that energy level, the energy of that eigenlevel, the chemical potential that you've set, and now instead of comparing that to -1, you compare it to 1 and invert it. That now is a smooth function which goes between 1 at low energy, 0 at high energy, and crosses over at the chemical potential. So that is 1/2 at that chemical potential. All right, we used those occupation statistics to infer the low temperature behavior of a couple different kinds of solids. Where those distinctions between bosons and fermions are important. Low, by low, what we mean is that the temperature times Boltzmann's constant is smaller or on the order of some characteristic energy gap in the system. Fluctuations in the energy are related to the heat capacity, and when you have a system which is at low energy, like an effective 2-level system, the heat capacity is just given by that energy gap squared. So that's the size of the fluctuation that happens in a 2-level system times the probability that it happens, the Boltzmann factor. And for solids where the dominant contribution to the heat capacity is from the lattice, from phonons, so that would be, for example, when I have a semiconductor such that electronic fluctuations or fluctuations in electronic energy levels or electronic energies are really small because I have to span a big semiconducting gap. We found that the heat capacity had a particular temperature dependence in agreement with experiment and with the so-called Debye model. The heat capacity scales like T to the 3rd. For solids, which are metallic, or where the dominant contribution is from electrons, There's a very different sort of scaling. In this case, the fact that fluctuations in a system of fermions are really pinned to where the Fermi level is. So particles deep at very low, fermions at very low energy are very unlikely to fluctuate because they have to find an empty state, which is only there for a very high energy, or much higher than where those low energy electrons are. Therefore, only electrons that are in energy levels close to the Fermi level, where the maximum occupancy level is, are going to contribute to fluctuations in energy. And in such a case, in this Fermi gas model, we found that the heat capacity scaled like the temperature. The Fermi gas theory, and invented by Enrico Fermi. So in a metal, for example, that lowest temperature behavior will be linear. And then eventually, even in a metal, phonons will become important. You'll find something that goes like T cubed. Finally, at high T, this distinction doesn't matter, and we find our normal Boltzmann distribution. For example, the average occupancy over the average number of particles is going to be given by our usual Boltzmann factor of that energy level, normalized by a partition function. Now, this should be stressed that this is high temperature and low density or small probability of occupying that ith level. Okay, so those are the quantum statistics results we derived last time. Now let's reflect back on a system of classical non-interacting particles. So we're imagining we're in this high temperature, low density limit where those distinctions between bosons and fermions don't matter. Okay, so what have we learned thus far? So absent interactions, a given particle has a number of ways that it can, a number of dynamical variables associated with it, a number of microstates just internal or just associated with that individual particle. For example, if it is in a box, a particle can sample different translational states by moving to different points in that box. If it's a point particle, that's all it has. However, if it is a molecule, like a dimer, like nitrogen gas, or a trimer, like water, not only will it have translations, but it will also have internal motion. And in a system that is non-interacting, those translations and that internal motion are independent. Where the particle is in space doesn't affect which vibrational or rotational state it can be in. Now, this is not true if particles interact. If particles interact, for example, I could imagine filling up space with particles. And so whether or not I am able to rotate or vibrate might depend on whether or not I have space to do that. So if particles are in my way, maybe I can't so easily rotate. But if there are no interactions, I don't sense my local environment. I don't know whether or not I'm in the middle of the box or near off center of the box. And so rotations and those translations, for example, are going to be independent. They're going to be uncoupled. A way of stating that quantitatively would be to say that a gas with internal structure for example, a water molecule, would have a single particle partition function little q that would factorize into a partition function associated with translations and a partition function associated with those internal degrees of freedom, where things like rotations and vibrations would live. So we know how to count up translational microstates, the number of microstates that a particle can sample in fixed temperature and volume is just given by the number of places I can put that particle, something that's going to go like the volume of the box that I put the particle in, within some resolution. And the resolution that we can use is just that thermal wavelength. This is no different from the very first problem set where I ask you to count the number of places I can put a particle in some lattice. Here we just know how to discretize space. We discretize space through the thermal wavelength. That has information both about quantum mechanical uncertainty. To what extent can I carve up space in terms of position and momentum such that I can't fundamentally distinguish individual microstates anymore. But in addition, it knows about thermal uncertainty. It knows about the typical speed a particle is moving over, which is just some simple function of the temperature and its mass. If I have that single particle partition function and I have a set of non-interacting particles, then the total in-particle partition function factorizes leaving me with a capital Q, which is equal to little q raised to the n over some factor in factorial accounting for the indistinguishability of those particles. And we saw last lecture how that actually comes out of the high temperature limit of quantum indistinguishable particles. But that single particle partition function has these two fundamentally distinct kinds of components. It has a component associated with where I can put that particle in space. That's our translational part. It was like V counted in some resolution. And it has this internal part that would have to do with what that particle is, whether or not it can rotate or vibrate. So if we broke up that total n-particle partition function in such a way, we could see, for example, that all of the volume dependence, all of the information about the extent of the system lives in the translational part of the partition function. And through that thermal wavelength, there is an explicit dependence on T, or an implicit dependence on T. That internal part of the partition function can depend on T. I have a Boltzmann-weighted sum over internal degrees of freedom, microstates associated with different vibrational or rotational states. But it is not going to depend on the volume. The number of thermally accessible states doesn't depend on, internal to a particle, doesn't depend on where in the box the particle is. That simple structure that tells me that there's a piece with an explicit V dependence, and that is the only V dependence, admits simple consequences for the thermodynamic properties of an independent particle system. For example, since we know that minus beta A is equal to log of Q, if we have lots of particles, then, for example, I can compute the Helmholtz free energy as N log V in units of that thermal wavelength plus N times log of the internal partition function. And using Stirling's approximation, an N log N plus N. So this first term here comes from the translational part of the partition function. This term here comes from the numerator of the internal part of the partition function, and then we have Stirling's. So that says that the Helmholtz free energy has these three different contributions. Apart from permutations, apart from translations, and apart from internal structure. And therefore, we can compute, and given that Helmholtz free energy, we know through the structure of thermodynamics that derivatives of that Helmholtz free energy will tell us about things like the energy, the pressure, and the chemical potential. So let's see how that works. So consequently, if, for example, we took the derivative of the Helmholtz free energy with respect to minus beta up to a factor of minus beta, we would get the average energy. In this case, that's going to be N times log d beta, or the derivative with respect to beta of log of Q internal over that thermal wavelength. That is because log V does not depend on beta. So if I take the derivative with respect to beta, that's just 0. A product in the log will just give me an additive contribution whose derivative is 0, so I don't even need to write it. This is therefore N times some function of the temperature. If, for example, all I have is a single point particle. Q internal is just one. There's only one microstate available internally. And taking a derivative of the log of that thermal wavelength will give me 3/2 kBt. But in general, that Q internal could depend on temperature, so I'll have some additive contributions to the average energy. So this sort of relationship is where equipartition comes from. So that sort of structure we've seen before. What about if I take the derivative of log Q with respect to V? That's going to be like taking the Helmholtz free energy, the derivative of the Helmholtz free energy with respect to V. That's going to give me pressure up to a factor of beta. If I take that derivative, the volume dependence is only here in log V. So I get N times the derivative of log V with respect to V. That gives me 1 over V. That indeed just pulls down a V times an N. I have beta pressure is equal to N over V, which is just the ideal gas law. And of course, the ideal gas law is independent of what kind of particle I have. So whatever internal degrees of freedom I have, because those internal degrees of freedom are not dependent on V, how I explore them doesn't depend on the volume of the system, that contribution is completely irrelevant for the relationship to the pressure. Ideal gas law holds for hydrogen gas as well as it holds for helium gas or for water vapor if those conditions of independence hold. All right, so Q is a natural function of temperature, volume, and number of particles. So what happens if we then take the derivative of log Q with respect to N? So that should be like taking the derivative of the Helmholtz free energy with respect to N, which will give us something proportional to the chemical potential. In this case, that difference in beta gives us minus beta times the chemical potential. And if we take that derivative, so where does N show up? I have two linear functions of N here and here, and then an additional function of N there. So I'm going to get a log V over lambda cubed, a log Q internal, and some factors of N. If I do that carefully, what I get is log V over N plus log Q internal over lambda cubed. Rewriting this, I could write this as the chemical potential is equal to kBt log rho. I take the minus sign over to the right-hand side. That gives me minus log N over V, which is log minus log V over N, which is log N over V. I can add and subtract this constant V naught, such that when I add it there and subtract it here, I'll get kBt log lambda cubed Q internal times V naught. Now that has a nice simple form. The chemical potential is linearly proportional to the logarithm of the density. And that's where all of the density dependence of the system exists. And this term is potentially complicated due to that Q internal, needing to sum up all the internal degrees of freedom. But it is still just a number. It's a number that's going to depend on T, but not V. Let's just define this. So the whole thing has to have units of, has to be a chemical potential. So let's call it mu naught of T and term it the standard state chemical potential. Essentially defined, one could think of it as being defined through that constant V naught that I added and subtracted. Because when rho is equal to 1 over V naught, that chemical potential is just equal to that standard state value. Indeed, this form for the chemical potential, derived from a set of non-interacting gas particles, has a known name. It's called the ideal solution form. Okay, so that's for gas particles, though. What if we had a dilute solution? So a set of solutes which did not interact with each other and can occupy different space in a liquid. So all the way back in the first day of class, when we thought about our ink drop, we discovered through a straightforward calculation that solutes in a solution obey the same sort of ideal gas law as an ideal gas, but the pressure was not the regular pressure, it was the so-called osmotic pressure. What are the consequences for a dilute solution for the form of its chemical potential? All right, well, let's set that calculation up in a manner analogous to what we've done in the past. So let's imagine we can take that solution, grid up space, where we have some length L that defines the size of that grid. And let's choose L large enough that each cell is uncorrelated. With its neighbor, for example, but small enough such that when I put solutes in it, the density for a very low density of those solutes, it's small enough that I'm likely to only have 1 or 0 solutes in any cell. So if I set n as the number of solutes in some cell, these take on values of only 0 or 1. So here's my liquid solution, my solutes filling some of those cells. For concreteness, let's imagine I have M cells in total, and let's take Q1 to be the partition function of a cell with a solute in it. That is likely a complicated object to compute because that solution, the solvent molecules in that solution have a number of microstates which come about and are sampled by very complicated intermolecular interactions. Nevertheless, I can, in principle, imagine that I could do that sum provided an energy function. And if I did that sum in the presence of a solute, the number of those states would be Q1. In the absence of a solute, the number of microstates, let's denote Q naught. So again, I can imagine summing over all the solvent microstates for a cell with no solute. If I did that, I would get the number Q naught. Now let's play the normal game. If the number of cells is much, much larger than the number of N solutes that I have, the partition function for the system will be the number of ways I could put N solutes in M cells, and in that dilute limit, it is just M to the N over N factorial. And each one of those cells in which I just put a solute will contribute Q1 microstates. There are N of them. Each of the cells that do not have a solute contribute Q naught microstates, and there are M minus N of them. I could rewrite this as M to the N over N factorial Q naught to the M times Q1 over Q naught to the N. Now, if I wanted to compute the chemical potential of those solutes, I still need only to compute the N, capital N, dependence of the log of the partition function. Doing so, d log q dn, as before, will give me minus beta mu. And in this case, taking that derivative in the limit that n is large gives me log m over n plus log q1 over q naught. Let's take V, capital V, to be m times L cubed. So those boxes each have a little volume, little L cubed, such that rho is equal to N over V. Then I can write that chemical potential as kBT log rho L cubed plus kBT log Q naught over Q1. Now look at that. That is the exact same form as we just arrived at for an ideal gas. I have a chemical potential that depends linearly on the log of the density. So all of the density dependence is in this term. And now I have another term, this term here, which is likely complicated, depends on all of the microstates that the solvent can exist in the presence or absence of a solute. So this likely depends on the temperature. It might also depend on the pressure, for example. but we can analogously define it as some number, some standard state, some mu naught. So just as we found long ago for the pressure for a system which is uncorrelated, that can perhaps have internal structure or not, the ability to count translational states independent from any internal states gives rise to the same form for the pressure in the gas or in the liquid, in a dilute solution or an ideal gas, as well as for the chemical potential. We talk about the ideal gas law since you were very young, because it's simpler to think through the pressure, but the ideal chemical potential is just as fundamental and just as ubiquitous, and just as useful. In fact, it, as we'll see now, underpins a lot of what you are taught early on in chemistry. That leads us to a discussion of mass equilibrium, which is really what the chemical potential tells you about. Okay, so let's see how we can use this result to understand mass equilibrium, which is just a question of where mass goes, which of course is going to depend on the chemical potential, because the chemical potential is the potential for mass to flow between two parts of a system. Let's first think about this in the context of partitioning particles, say, between phases. Okay, let's imagine that I have some system that has a vapor up here, a liquid down there, and within both the vapor and the liquid are some solutes that can exchange. At equilibrium, what must be true? So if the system's at equilibrium, that means that the temperature of that vapor and the liquid are the same. So TV for vapor must be equal to TL for liquid. Otherwise, energy would be flowing. It must be the case that the pressures are equal. Otherwise, the volume would be flowing. So PV must be equal to PL. The pressure of the liquid must be equal to the pressure of the vapor. And for there to be no net mass change, it must be that the chemical potential of a liquid is equal to the chemical potential of the vapor. But that must be true for each species. So whatever makes up my liquid and vapor, maybe it's water, in addition to whatever those solute particles are. In fact, that condition, that mu V is equal to mu L, controls the distribution at equilibrium of solutes in the liquid and the vapor. If we imagine that the solutes are dilute both in the vapor and in the liquid, Then we can use those ideal forms for the chemical potential to actually understand what is the concentration of the solutes in the vapor, say, relative to the liquid. So this condition here, the equivalence of the chemical potential, which must be true at equilibrium, stated in terms of those equations for the chemical potential. So for the vapor, we had that the chemical potential of a vapor was kBT log, let's go rho V for the density of those solutes in the vapor. That was multiplied by some thermal wavelength and had a term due to any internal degrees of freedom, like so. That's the chemical potential of the vapor. Must be equal to the chemical potential of the solutes dilute in the liquid, which was kBT log rho in the liquid, say in some reference volume L cubed, and had some contribution due to those microstates in the presence or absence of the solute. If we then solve, so we can divide through everywhere by kBT, exponentiate everything and solve for the ratio of densities, and what we'll find is that rho L over rho V, so the density in the liquid relative to the density in the vapor, are units of length, thermal wavelength in one case, this L cubed in the other, and these factors of partition functions, Q1, number of microstates in the cell with a solute, over the number of microstates in a cell without a solute, times those number of microstates internal to the gas. So what have we just found? That relative concentrations in one phase or the other is equal to a number. That number is what you'd call KH. That's Henry's law. That's what determines the, how fizzy your carbonated beverage of choice is. If I have some concentration of solutes in the vapor, well, concentration or density is always equal to a pressure, so I could write that in terms of a pressure. Applying some vapor pressure of, say, CO2, if I know that Henry's law constant, K sub H, I'll know how much CO2 is solubilized in the liquid. In fact, if I could just do the counting, count up the number of microstates Q1, Q0, and Qint, I could predict the Henry's law constant. In fact, going a little further, if we were to choose L cubed in the vapor, so we grid up the vapor and count translational states in that way, such that the number of states in a cube of length L in the vapor would be some ratio of thermal resolution to that L cubed times that internal set of microstates. Then we could rewrite this ratio rho L over rho V as Q1 over Q naught times QV. So that ratio of densities or concentrations is equal to the number of states in a cell of length L cubed of the solvent, where that solute is present, over the number of states that that solvent can sample in the absence of the solute, plus the number of states for the solute in just the vapor. So that's in pictures, in words, the number of states with solute in solution relative to the number of states with the solute in the vapor. So the Henry's law constant is just a simple number, the number of microstates when I have that solute pulled into solution over the number of states when that solute is in its vapor. Any ratio of partition functions has an interpretation as a change in a free energy. These are constant temperature and volume free energies, Helmholtz free energies, so that is also then representable as a reversible work. In this case, the reversible work to drag a solute from the vapor to the solution, into the solution. So if I could actually microscopically grab onto a solute, say that CO2 molecule, and compute the work to reversibly move it from the vapor into the liquid, that would actually give me a means of predicting the Henry's law constant, of predicting the partitioning of that solute between the liquid and the vapor. Again, this is a consequence of the fact that we have independent particles, so we can separate all of the volume dependence of its partition function, and therefore its chemical potential, away from internal degrees of freedom. This does not hold if the system is interacting in such that we cannot factorize the volume, the translational dependence from the other internal degrees of freedom. Okay, so that's that's an example of mass equilibrium where a solute is likely to go between two phases. We could analogously consider a case of equilibrium between two different kinds of molecules, like one would have in a chemical reaction. Consider, for example, the reaction that capital B molecules reversibly transform into capital C molecules at fixed temperature and pressure. Let's imagine repartitioning delta N molecules between those B and C forms. Where this delta N is small. If we did that, if we ran that reaction slightly forward, if I had NB molecules, well then I'll lose B times delta N of them. Analogously, if I initially started with C molecules, I will gain C times delta N new C molecules. The likelihood that this is going to happen is going to be determined by the Gibbs free energy because I'm at constant temperature and pressure. The change in the Gibbs free energy as I advance this reaction forward a little bit is going to be a sum of how the Gibbs free energy changes through a small change in NB molecules at fixed temperature, pressure, and number of C molecules, times how many B molecules have just changed, plus the corresponding change in the Gibbs free energy due to changes in C at fixed temperature, pressure, and in B, which is going to be plus C times delta N. This, get some color in here, how the Gibbs free energy changes with NB molecules is what I would mean by the chemical potential for B. How it changes with C is what I mean by the chemical potential for C. This is equal to 0 at equilibrium. If I'm at equilibrium, therefore, those sum to 0, so minus B mu B delta N plus C mu C delta N is equal to 0, or B mu B must be equal to C mu C. That is a condition of equilibrium. We can, in fact, pretty easily generalize that for a more complicated reaction. If, say, A molecules meet B molecules to make C molecules, and D molecules, the structure will be the same. I'll take A times the chemical potential for A plus B times the chemical potential for B. The condition of equilibrium will be that that is equal to C times the chemical potential for the C molecules plus little d, its chemical potential. Now, if all of these species are dilute, and we assume, for example, that V naught is the same, or the reference standard state is the same, if they're all dilute, then they're all going to have this ideal form for their chemical potentials. So plugging it in, for example, for this B molecules going to C molecules, I'll have B times the standard state chemical potential for B plus KBT log the density of B, say in some reference length L cubed. At equilibrium, that will have to be equal to C times the standard state for C plus KBT log the density or concentration of C, or rearranging rho B to the B over rho C to the C is going to equal, at equilibrium, L to the minus B plus C cubed factors of that length times e to the minus beta delta mu naught of the reaction, where this delta mu naught of the reaction is equal to B factors of mu B, standard state, minus C factors of mu C standard state. What have we done now? We have the relative concentrations of reactants to products raised to their stoichiometric integers is equal to a number over on the right. That number over on the right is typically what we call the equilibrium constant. The really fancy name for this result is called the law of mass action. If we specialize to the case where this reaction was happening in the gas phase, for example, then that equilibrium constant has a simple form. It's going to be the internal degrees of freedom for C over C's thermal wavelength raised to the C over the number of internal degrees of freedom for B over B's thermal wavelength cubed raised to the B, which I find super interesting. That tells you that if you could just count up the number of ways a particle can be, the number of internal states, you can predict the equilibrium constants of systems. And indeed, that's a very viable way to do. You've already explored that for a simple reaction of H plus H goes to H2. You might acknowledge or might intuit that for more complicated molecules, doing that counting is maybe hard, but a computer could probably do it. In fact, a very reasonable way to compute equilibrium constants is to ask a computer to sum up those states in clever ways. That is essentially the endeavor of much of computational drug screening. One can just count up in a clever way the number of microstates of a ligand bound to a protein relative to that protein and that ligand in isolation, and thus predict the binding affinities of ligands. Even if, an important point to note is that these specific relationships for densities assume, so this form of equilibrium constants that we all know or all taught in introductory chemistry classes, that implicitly assumes dilute solutions. It's important to recognize that even if the system is not dilute, it still must be the case that B times the chemical potential of B is equal to C times the chemical potential of C. Or that if I just exponentiate both sides, multiply by a factor of beta, that is true. So the complete chemical potentials are equivalent of the stoichiometric constants at equilibrium, and in the case where the dilute solution holds, we just have a clever way of separating out the density dependence of the chemical potential from all of the other pieces. But even in cases that aren't so simple, when solutions aren't so dilute, one could define a so-called activity. Let's say for species J as e to the minus beta mu J less its chemical potential at some standard state, which may be some complicated function of the density now, because if it's not dilute, we can't factor out the density in such a clean way. Nevertheless, if we define it such that in the limit that rho goes to 0, that activity goes to rho up to some factor of v naught, some standard states, we'll get back such that we get back the ideal form. Let's say if, as this is true, then we'll reduce to the ideal form. That means that for a reaction at equilibrium, we can still write the ratio of activities, say for species B raised to the B or C raised to the C, is some equilibrium constant, which in this case is still equal to some chemical potential of that reaction. So we can kind of fudge that density dependence by redefining an activity such that it knows about the full chemical potential. So those of you who remember your quantitative chemistry class, when you had to introduce activities, those were essentially accounting for the fact that there are corrections to infinitely dilute solutions. That's a very thermodynamic perspective. In fact, a lot of this was kind of a thermodynamic perspective on the chemical potential. I want to wrap up by starting to think a little bit about a more molecular basis for these, say, equilibrium constants. Let's, for example, consider the binding of B to C in solution. Such that B plus C goes to a complex BC. So what would this mean molecularly? So let's imagine we have, say, a solute B and a solute C that are separated in space by some vector R and in solution. Let's define what we mean by a complex. If that separation distance magnitude of that vector R is less than or equal to some R star. Now, let QR be the partition function when B and C are separated by some distance R. Q, just a number of states weighted, just the sum over states weighted by the Boltzmann factor for each one of those states, I can fix or decide to sum only those states consistent with B and C being separated by some distance r. That would give me QR. And let's write or express that partition function as e to the minus beta, some reversible work function of R. So again, a partition function is always proportional to or related to a Helmholtz free energy, which always tells you about the reversible work accessible to a system. Now let P of R less than R star be the probability that R is less than R star. That probability is just integrating over all R for R's less than R star, the number of states at that R relative to the total number of states, which if parameterized by R is just a sum over all possible R, say in some fixed volume. Now this is vector R. If it's spherically symmetric, I can integrate out the angles. That'll give me 4 pi, an integral from 0 to R star, R squared dr, e to the minus beta, this reversible work function. Let's not give that a subscript. Now, as long as, so there will be some value of that function, some constant, that is what happens at large R. If I'm integrating over a macroscopic volume, any of the wiggles before it gets to that constant, as long as that constant happens sufficiently close, are going to be dominated by the integral where it's just a constant. In fact, this will go to just a factor of the volume. So putting that together, I have 4 pi over V, an integral up to R star, R squared, and let's take this constant upstairs, so it's now e to the minus beta delta W of R. If we have many C's and B's in solution, then the number of complex BC's at some given time is the number of B's times the probability that a given B is complex. In which case the number of complexes is the number of B's times the number of potential partners C's times the probability that B and C are, a given B and C are within R star of each other. So the picture we have in our mind is we have lots of B's, lots of C's, and some BC's. We have an explicit form for that probability, so the number of BC's is the number of B's times the number of C's times 4 pi over V times this integral from 0 to R star, that Jacobian for spherical coordinates, and this reversible work function. Just clean this up a little bit. So if I take this expression and I divide by v on both sides, I have rho BC is equal to rho B, and I can pair this volume with rho C times this factor 4 pi. I don't have a V anymore. And I have this integral up to r star. Or rearranging, I have a ratio of the number of BC's to the number of B's times the number of C's is now 4 pi times this integral, summing up the reversible work to move those BC's relative to each other. If we take that work to be, say, minus epsilon for r less than r star, and 0 else, so there's some attractive interaction if they're close to each other, otherwise they don't feel each other, then that's an integral we can do. It'll give me 4 pi over 3 r star cubed e to the minus beta epsilon. Now, what have we just done? We've actually just solved for microscopically for that equilibrium constant. In which case we can note that the effective volume, that standard state that has come in, is the characteristic scale over which those particles interact. So again, the microscopic perspective of an equilibrium constant really is just the reversible work to arrange those particles in that product state. So bringing a B relative to a C reversibly, which can be, maybe difficult to measure. Maybe if you have optical tweezers, you could actually perform such a transformation. But certainly on a computer, one could imagine doing that. And if one could, then you would know the equilibrium constant associated with that transformation. Again, this has been a little more opaque, but this too assumed a dilute solution of B's and C's, such that we had this simple factorization of the likelihood of forming a B-C complex as just the number of B's times the numbers of C's. But now just on a slightly more microscopic perspective. All right, well, that's all I've got for this lecture. We'll continue on in our discussion of chemical potentials and mass equilibrium, though next lecture we'll start moving into questions of mass equilibrium in the context of phase transformations. So stay tuned for that.